Let's move on to section 4 and function. We talk about linear functions and models utilizing the linear. Let's take a look at linear functions, how to use a linear function to model the real life scenarios, real life applications. Linear function, so basically we are dealing with this is base model we are using to capture the model using the linear function. And we're also going to take a look at some mathematics applications in real life. So first of all, let's look at the mathematical models, how people come out with mathematical models and then use a linear function to analyze the mathematical models. So regardless of field, problem is solved by analyzing the process called mathematical modeling. So there are 4 steps in this process. First of all, we have a real world problem, real world application. So we formulate mathematical models. In this case, we use the linear function MXB. And then after that, we solve for typically we solve for slope and y-intercept. And once we know both of them, we have a linear model, and we use to interpret real problems. We also do some tests, make sure we satisfy all of the requirements. So that's a process of creating the mathematical models using linear function. And function, we're using f of x for example function called f of. Keep that in mind. F of x is the same thing as 1. Remember, for the from the previous sections, we have y equals mx b. We call this slope intercept form of linear equation, slope intercept. Equation. And when y becomes f of x, linear function, it becomes linear function. F of x is a function. It's what we call a function notation. So anytime we see f of x, means we're talking about a function. Now, let's look at a couple examples about the functions in real life. The manufacturer would like to know how his company's profit is related to the production level, how many number of units produced determines the profit produced in the manufacturing sector. Also, biologists would like to know how the population of a certain bacteria will change with the time. So here the time t, that's time t is dependent variable. Number of the bacteria becomes dependent variable. Number of bacteria called dependent variable. So typically, number of the bacteria depends on the time t. And we try to fit a model to analyze. Similarly here, number of units produced is dependent variable. and the company's profit is dependent variable, meaning profit depends on number of units produced. Now, in each case, we are concerned with the same question: how does one quantity depend on another one? And this one quantity is called an independent variable. So one quantity is called dependent variable. The relationship between two quantities conveniently described in mathematics by using concept of function. And one function is a rule that assigns to each value of the x only one value of the y. Meaning a function is one-to-one relationship. One-to-one relationship between two variables. Those two variables are independent variable and dependent variable. And we try to figure out a relationship between those two variables. The mathematical model. For example, right? As I mentioned earlier, y equals and y is the standard notation. F of x is the function notation. There's a difference between those two notations. Number y is normally denoted by f of x with f of x, emphasizing dependency of y on x. An example of a function may be drawn from a similar relationship between the area of the circle and the radius. Right? Let's assume the area of the circle as dependent variable y, radius as independent variable x. So x represents radius, y represents area of the circle. So from the elementary geometry, we have area equal to pi r squared, right? So it becomes pi x squared. So here x represents radius, and then y represents area, circle. Now let's do a little bit of analysis on this. So given this area formula, if let's say radius is 5 inches, that means x equal to 5 inches. Now from here, we're going to replace x with 5. We're going to get this. The area of the circle equal to f of 5, because f of x to 5 times x squared. Here, when x equal to 5, placing x with the 5. We get pi times, so we have f of 5, x becomes 5. F of 5 equal to pi times 5 squared, which is 25 pi. So, radius equal to 5 inches, then the area is 25 pi square inches. And suppose we are given the function y equal to f of x. So basically we have a variable x is independent variable. Variable y is the dependent variable. Y depends on x. And the domain is all possible x values. The range of all possible y values. So let's just give us a couple of important notation here, right? So that's related to the linear equation now. When d is not 0, the equation can always be solved for y in terms of x. So get y equal mx, call this slope intercept form, right? And here m represents slope, b represents the y intercept. Okay. And we can also write it as function notation by changing y to alphabet equal to mx. So now this is a function notation, and the domain for this linear function is all real numbers, and the range is also all real numbers. So let's look at the function notation for linear function here. For f of x equal mx plus b is called a linear function. In this case, both m and b are constant, and m represents slope, and b represents y-intercept. And once we know both of them, then we know the linear function. Linear function could be utilized in different fields, especially in business and economic fields. There's a lot of linear functions for quantitative analysis. And let's take a look at one of the real-world applications of the linear function. It's called simple depreciation, or accounting terms called accounting field of finance. It's called streamline depreciation. Streamline depreciation. It's very important accounting term. Basically, the linear function to model the depreciation of the assets. Okay, so the following example illustrates how to derive an equation describing the book value of the asset, and also annual depreciation, right, using the linear function. Basically, we are going to use this particular model of y equals mx plus b to capture the depreciation process. Let's look at it. Let's say you work in a network company, have a network server, has original value of $10,000. Meaning, when the network company purchased the network server, it cost $10,000. So this actually gives us an initial condition when time t equals 0, then the value of the network server is equal to $10,000, the initial condition. And this network server is to depreciating linearly. So this tells us the linear depreciation over 5 years with the $3,000 residual value. So in time t equal to 5, now the value of the machine becomes $3,000, meaning after 5 years, value of the machine drops $7,000. Find expression using the book value at the end of the year t. What will be the book value of the server at the end of the second year? What is the rate of depreciation of the server? So first of all, we are given two conditions. First one is, so we're assuming time t is independent variable. So here time t should be independent variable. Time is always an independent variable. Time doesn't depend on anything. And then value of the server value, using v to represent the value, it's a dependent variable. So value of the server depends on the time. As time goes by, the value of the server drops. And we try to figure out how fast the value of the server drops or decreases over time. So we are given two conditions. First one, as I analyzed earlier. So when time t equals 0, then we get $10,000 value. When time t equal to 5, then the value drops to $3,000. So V is a linear function of t. So first of all, we're going to find out the slope. To find the equation of straight line, observe that V equal to $2,000 when time equal to 0. So you get this order pair 0,000. And second condition is when time t equal to 5, then value of the machine equal to $3,000. You get a second order pair. Now from there, we can come out with the slope. Slope equal to, we're going to these two order pairs 0, 2,000, 5, 3,000. And as we talked about earlier, slope formula is y2 minus y1 over x2 minus x1. Here, label this x1, y1, x2, y2 for second order pair. So replacing all the values, all the variables with a given value, so we get 3,000 minus 10,000 divided by 5 minus 0, negative 7,000 on top, divided by 5. So this is negative $1,400. Denominator is years, so it's $1,400 per year. This tells us that as the time increased by 1 year, as time increased by 1 unit, 1 unit is 1 year, then the value of the network server decreased by $1,400. Decreases by $1,400 per year, right? That's what the interpretation of the slope. So now, since we know slope is negative 1,400, so we are given order pair x1, y1. As you can see, when x equals 0, then the y-intercept b, this tells us y-intercept b equals $10,000. So the linear function will be written as f of x equals mx. So now plug in the slope, plug in the y-intercept b, and get a linear function. Right? We utilize the model of this f of x equal to negative 1,400 x plus 10,000. And here the dependent variable is v of t, right? Value of the server. Independent variable x is time t. So if we apply to this particular scenario, we can use this model to represent relationship between time t and the value of the machine. And now the book value at the end of the second year, since we know v of t, 1,400 t plus 10,000, given t equal to 2, placing t with the 2, we get negative 1,400. 2 times 10,000, and that's negative 2,800 plus 10,000. Combine them, we're going to get 7,200. Meaning, after 2 years, the value of the machine, the book value of the machine at the end of the second year is 7,200. The slope, we already analyzed it. It's the rate of depreciation here is 1,400 per year. Scenario. And if you draw the graph, 0, 10,000, that's the initial point. Second one is when time t equal to 5, value of machine 3,000. You connect them and you get a linear model you utilize to describe the relationship to those two variables. And notice that here the time t cannot be negative. So actually on this side we see dash line because time t has to be between 0 to a certain years. And also after this machine will be fully depreciated after 7 years. That's 7. Between 7 and 8 years, the value of the server will depreciate to $0. And that's also another part of the story here is eventually the value of the machine will has a value of 0 after the full depreciation. If you want to know when the value becomes 0, to be exact, you can set v equal to 0. I mean, the value of the machine equals 0, that means negative 1400 times t plus 10,000, that equals 0. That comes from the linear function. Now we solve for time t by subtracting 10,000 from the equation. So we end up with negative 1400 t equal to negative 10,000. Now we're dividing negative 1400 from both side equation. And so that time t is approximately equal to 7 point something. 10,000 by 1400. We can reduce it to 100 by 14. That's 98. So 2. So it takes about 7.1 years, right? 7.6. Got a 0 here. Another 0 in the back. 14 going to 60. That's 4 times. So that's about approximately 7.4 years. Meaning between 7 and 8 years, the book value of the machine becomes 0. Now let's take a look at another important applications in the business field. It's called linear cost, revenue, and then profit functions. 3 different functions: cost function, revenue function, third one is profit function. And we're going to model all 3 functions using a linear function. Now we're going to take a look at some concrete examples about this. So first one, let's get familiar with the terms. What's the linear? Cost function, revenue function, profit function. Cost is the cost of producing a product, X units of the product, right? So X represents the number of units of a product manufactured or sold. So the total cost function, C of X, C is the abbreviation of the cost, right? C of X. The total cost of manufacturing X units. They're producing X units of the products. And the revenue function, R of the X is total revenue generated from the sale of X units of product. Profit function is the total profit realized from manufacturing and selling X units of product. Total profit, P of X. Right? So we have C of X, cost function, revenue function, profit function. Profit function actually is equal to profit equal to revenue minus cost. So basically it's R of X minus C of X. The relationship between cost, revenue, and profit. So generally speaking, the total cost, revenue, and profit function cannot be modeled using linear function, but linear cost, revenue, and profit function does arise in the real world scenarios. So for this particular section, we're assuming cost function is linear function, revenue, profit function are also linear functions. So before we start deriving all these different revenue function, cost function, profit function, what's the common terminology? You can say cost sector. In the cost field, we have something called fixed cost. Fixed cost maybe means the cost remain constant regardless of the production level, right? So A concrete example could be rent, right? Rental fees. Let's say you are producing like garments in a warehouse, and the rental fee of the warehouse is what we call a fixed cost. And also, let's say you hire some production manager to supervise the production process, and that production manager's salary is also fixed cost. It remain constant month over month, right? Because the exact salaries or production manager's salary is fixed. Those are the example of fixed costs. Also, the cost, sometimes some of the costs could be a variable cost because they vary with the different production level. Example, variable costs are wages of the production worker, right? Wages of the worker. For example, if let's say John works 10 hours in a week 1, and week 2 he works 14 hours, then you see that our hourly salary changes week over week. So depends on production level. Also, the cost of the raw material is also an example of the variable cost. Producing more units, then you use more materials. The cost of the material will be more. Suppose a firm has fixed cost $F, production variable cost $C per unit, a selling price of X per unit. So meaning basically this company has a fixed cost $F, production variable cost $C per unit. So the cost function should be C, that's variable cost, times quantity produced, X, assuming X represents quantity produced and sold. So C times X represents total variable cost, plus F is fixed cost. So this pi is variable cost. F is the fixed cost. By those two costs, total cost. Revenue function is equal to you selling the unit at X dollars per unit, S times X units sold. So it's X times X. Profit function equal revenue function minus cost function. So we have X times X minus parentheses C times X plus F. Expanding, we get S of X minus C of X minus F. Here, X represents number of units of the produced and sold. Right? We have cost function, revenue function, profit function. They are linear function of the variable X. And that's basically how we utilize the represent each revenue function. Now let's take a look at a real world scenario. Let's say we have Puretron, manufacturer of water filters. Monthly fixed cost of $20,000, a production cost of $20 per unit, selling price of $30 per unit. Find the cost function, revenue function, profit function. So cost function first. Cost function we're using C of X equal variable cost, which is $20 per unit times X unit produced. So that's assuming X represents units of water filters produced and sold. Units produced. So assuming all units produced are sold at the same time. So C cost function equal to variable cost $20 per unit times X unit produced and sold, adding a fixed cost $20,000. Okay, so that's the cost function. Now the revenue function. So since each unit is sold at $30 per unit, so revenue out X $30 per unit. If you sell 1 unit, you get 30 times 1, $30. You sell 10 units, you get 30 times 10, $300. If you are selling X units, it would be 30 times X. So that would be 30X. And then the profit function. Mentioned earlier, profit function P of X equals to revenue function minus cost function. That would be 30X minus 20X plus 20,000. Expanding, you get 30X minus 20X, 20,000. Combine like terms, 30X minus 20X equals 10X. Get all three different functions, right? Say you have a so we can come up with a cost for revenue to the profit. Okay, now let's take a look at another more scenarios. Consider a manufacturing process produce 7,500 units at a cost of $650,000. 10,000 units at a cost of $850,000. Each unit produced could be sold for $100. Assuming a linear relationship exists between the number of units produced and the cost. Find the total cost function, revenue function, profit function, given a unit of the slope and y-intercept. Secondly, find the variable cost per unit, also known as marginal cost. Also find the total fixed cost. Third step, the cost, revenue, and profit when 60,000 produced. And after that, let's find the break-even point. Break-even point indicates no profit. Break-even is no profit, no loss. And average cost per unit producing 25,000 units, and the equation of the average cost per unit function. So this is very comprehensive problems with respect to this manufacturing process. So let's, I'm going to put it into another platform. We can analyze from here. Okay. So first of all, we're going to into this. First one is the cost function. One time cost function. Alright, so now we are given two conditions. We're producing when X equal to 7,500 units. The total cost B of 7,500, that's equal to $650,000. And second condition is when the total units equal to 10,000 units. Total cost for producing 10,000 units is $850,000. So basically, knowing two given conditions, find out the cost function from there. Alright, so basically we are given two order pairs. First one is 7,500, cost is 650,000. Second condition is 10,000 units. Total cost is $850,000. So now let's look at the cost function first. So let's find the slope. So this is x1, y1, x2. So slope m equal to y2 over x2 minus x1. So this is 850,000 minus 650,000 over 10,000 minus 7,500. So this turned out to be 200,000 over 2500. And this turned out to be 80 per unit. So meaning the variable cost per unit is $80 per unit. From here, we'll be able to find out the cost function using the function notation. And we go from there. So next step is finding cost function. So now we're going to use the this y minus slope. From here, we know slope, $80. X1 is 700, Y1 650,000. Okay, so we're going to plug into this points law form and go from there. So here we get a y minus 650,000 equal to slope 80, x minus 7,500. And we distribute it. We get y minus 650,000 for 80x 600,000. Multiply 8 by 75. 180 by 100 is 600,000. And we're adding 650,000 from both sides equation. And so that we get y value 80x equals 50,000. So this is what we call the cost function. So y is the same thing as c over x. So cost function is 80x plus 50,000. So here the variable cost per unit. Variable cost per unit. It's 80. And $80 per unit. And then the total fixed cost is $50,000. So here the y-intercept represents fixed cost. So you take care of the cost function. Now next step, let's take a look at the revenue function. So if you go up a little bit, in the question it tells us that each unit produced could be sold for $100,000. Revenue function here. Our each unit sold for $100. X unit sold, so 100 times X. Then here, slope m equal to it's profit. I mean revenue per unit, right? So each unit is sold for $100. Revenue per unit. And when does that be? Not sell any units, products, so you get $0 revenue. Revenue when X 0 unit sold. And we also have profit functions. So let's take a look at profit functions. Profit equal to revenue minus cost. P of X is R of X minus C of X. Total revenue minus total cost. Total revenue is 100x. And total cost, we already did it, it's 80x plus 50. So from here, when we distribute it, we get a profit is 100x minus 80x. So here we end up with a 20x minus So this is a profit function. So here, slope m equals 20, and that represents the profit per unit. $20 profit per unit. And if there's a 0 unit produced and sold, then company have a loss of maybe $50,000. So we when 0 units produced and sold, then it's $50,000 loss. So those are the 3 different functions. So take care of part 1, right? And then second step is called variable cost per unit. So variable cost per unit, we get it from the cost function, which is $80 per unit. Variable cost per unit, $80 per unit. And this is also called variable cost per unit, is called marginal cost. The fixed cost, also mentioned that is when there's a 0 unit produced, there's $50,000 of fixed cost. The fixed cost here will be $50,000. And the cost, revenue, and profit when 60,000 units are produced. So at this production level, let's take a look at all 3 different functions. Part 3, when x equals 60,000 units, cost function 60,000, 80,000 plus 50,000. So the total cost of producing 60,000 units will be 480,000, or 4,800,000 plus 50,000. This should now be $4,850,000. And then the revenue function, revenue producing 60,000 units, is going to be $100 per unit times 60,000, which is going to be $6 million revenue. And the profit of producing 60,000 units is equal to 20x, x is 60,000 minus 50,000. $1,200,000, 50,000, $1,050,000. We find the difference between the revenue and the cost. It's also $1,150,000. So this is cost, revenue, profit at this production level of 60,000 units. And part 4 is called the break-even point. Break-even indicates when profit is part 4 is break-even point. Break-even means no profit, meaning profit function is 0. We know that profit function is 20x 50,000. 0, then we can solve x. So add 50,000. So the equation, so we get 20x equals 50,000. From there, we divide 20 by 2,000, 2,500 units. When the company produced 2,500 units, they have break-even point. They do not have any loss profit. This is part 4. Part 5, average cost per unit of producing 25,000 units, the equation of the average cost per unit function. So first of all, let's find out the total cost of producing 25,000 units, 2,500 units. So total cost of units, 25,000 units. So you're going to plot the x equal to 1,000 into the cost function. So C of 25,000 equal 80 times 25,000 adding 50,000. That's 2 million plus 50,000, so it's 2,050,000 total cost. Now from here, average cost per unit. So it will be 2 million total cost by per unit per 1,000. And then if you divide into that, you end up with $82 per unit. Average cost per unit, 25,000 units produced, $82 per unit. And the average cost per unit function, we represent average. So A of X equals total cost C of X by unit. So C of X will be 80X plus 50,000. We come up with the general form of the average cost per unit function. And that's pretty much everything on this section. You should look into the back of the textbook and go into the details of calculation in terms of dealing with the cost function, revenue function, and profit function. Very, very important topic in the production process.